In computer architecture, pipeline hazards are situations that prevent the next instruction in the pipeline from executing during its designated clock cycle. This can lead to stalls or delays, reducing the efficiency of a pipeline processor. What is pipelining? Pipelining in CPUs is a technique to increase instruction throughput by dividing the processes of executing instructions into multiple stages. Each stage in a pipeline completes a part of an instruction, allowing several instructions to be processed simultaneously in different stages. Importance of pipelining: increased throughput. Pipelining enables multiple instructions to be processed at once or simultaneously, increasing overall throughput. Improved improved clock speed. Shorter pipeline shortages allow for higher clock frequencies, boosting processor speed. Resource utilization. Pipelining maximizes hardware resource usage, enhancing overall CPU efficiency. What are pipeline hazards? As we saw before, pipeline hazards are situations that prevent the next instruction from executing in the clock cycle. Which just begs the question, why are pipeline hazards a concern? Pipeline hazards occur when the next instruction can't execute in its designated stage because of conflicts or dependencies. Hazards cause pipeline stalls, reducing efficiency and slowing down the processing speed. Types of pipeline hazards. We have three types of pipeline hazards. They are structural hazards, data hazards, and control hazards. Data hazards, they happen when instructions depend on the data being produced by previous instructions that hasn't been completed yet. These are three types of data hazards: read after write, or RAW, reading data before it's being written, or WAR, write after read, writing data after it's being read. WAW, write after write, writing to same location twice. Raw hazard. This is a latter instruction that needs data that a prior instruction is still writing. Basically, this is the process that goes on. Take a look. WAR hazard. A latter instruction writes to a location a prior instruction is still reading. These are less common, and WAR hazards are less frequent in simple pipelines due to in order instruction execution. WAW hazard. A latter instruction writes to a location another instruction is still writing to. This can lead to incorrect results if the instructions are completely out of order. Proper instruction scheduling and register renaming techniques can help avoid WAW hazards.
So let me explain about the pipeline hazards in CPU design, where the challenges faced by the CPU design by affecting the performance and its efficiency. So the types of structural hazards, at first comes the structural hazards, which has caused the resource conflicts such as share resources, timing conflicts, and performance impact, where multiple instructions complete at the same time. So there is an hardware component issues and the timing conflict such as instructions require some same clock cycle which cause delays. And third, the performance impact, which leads to an pipeline stalls and reduced to throughput. Control hazards and branch mispredictions. Branch encountered, prediction made, misdirection directed, and resource files. Pipeline encounters and conditional branch instructions, outcome unknown, and which misdirection can lead to branch outcome prediction and causing pipeline fush. Causes of pipeline hazards. Resources conflicts, data dependencies, and control dependencies. These are the major causes of pipeline hazards, where multiple instructions complete for limited hardware resources, data dependency, where instructions rely on results of previous instructions, and control dependencies such as branching instructions create uncertainty in instruction flow. Solutions to pipeline hazards such as forwarding, stalling, and branch prediction. Forwarding, where we can directly pass between pipeline stages to resolve the data hazards, and stalling is where temporary pause pipeline execution to allow data dependencies to resolve, and branch prediction, where predict the branch outcomes to reduce the control hazards and maintain pipeline flow. And forwarding, let us discuss about the forwarding, where resolving data hazards, hazard detection, identify data dependencies between instruction and pipeline stages, and bypass the path, create the direct from producing the instructions to consume instructions, and fast data transfer, where the data is transferred to the computer and to the registers. Reduced stalls. Minimize pipeline stalls by providing data as soon as it is available to use. Stalling. Stalling is known as for the pause of resolution, where the hazard is detected and the stall is initiated and the hazard is cleared and resume the further execution. Where the pipeline controls the unit of which is the identifies the hazard and it inserts as the stall and which later the hazard is gets cleared and resume the execution of the solved problem. Branch prediction and mitigating control. So the prediction of the branch of the hazard that which can control the hazards are static prediction, dynamic prediction, and neural branch predictions. Where static prediction always predict the taken or non-taken branch type, where dynamic prediction use the history to make the predictions, and neural branch employ machine learning algorithms of prediction. Whereas the neural branch is an high accuracy and modern high performance processor. And at last, for the solutions of the hazard, we need to look after the three major points: out of the order execution, speculative execution, and simultaneous multithreading. Out of order execution, where the instructions, as soon as they are operand ready, they are used for the program. Speculative execution, where the executive instructions being known for reading and improving the performance in branching scenarios. Whereas the simultaneous multithreading execute multiple threads concurrently utilizing ideal pipeline stages during the hazards. Thank you.